To operate, quantum computers require extreme cold. This dilution refrigerate uses helium isotopes to cool the processor quantum computing needs.
Welcome to Module 4. In this video, we will explore the cryogenic system infrastructure that makes quantum computing possible by creating the coldest places in the known universe. It's prepared by Dr. Qureshi from National University of Singapore. He is currently working in the area of quantum computing hardware. To understand the need for such extreme cold, we must look at why room temperature acts as an enemy to quantum coherence. Everything vibrates with thermal energy at room temperature. For a quantum processor, this acts as noise that causes decoherence, or the loss of fragile quantum states. Absolute zero isolation is essential. Cooling is not just about reducing noise, it is about changing the state of matter. Metals in a quantum processor only achieve superconductivity near absolute zero. A cryostat serves three main goals: providing superconductivity, ensuring thermal isolation, and offering magnetic shielding to protect the sensitive qubits. Let's take a closer look at the dilution refrigerator, often referred to as the iconic golden chandelier of quantum hardware. When you see a quantum computer, you are typically viewing a dilution refrigerator with its outer vacuum shells removed, revealing the gold-plated copper plates and intricate cabling. The refrigerator operates across multiple stages, ranging from room temperature at the top down to just 10 to 15 millikelvin at the mixing chamber. To grasp how cold 15 millikelvin is, consider that deep space itself is 2.7 Kelvin. This makes the interior of a quantum computer one of the coldest spots in the universe. Now let's dive into the physics of how these dilution refrigerators achieve such extreme cooling. Below 1 Kelvin, standard cooling methods fail. Instead, we use the unique quantum properties of helium-3 and helium-4 isotopes, which spontaneously separate into two liquid phases. Cooling happens in the mixing chamber at the phase boundary. Pumping helium-3 atoms across this boundary creates an endothermic effect, absorbing heat from the processor. Beyond active cooling, we must also focus on physical isolation and shielding to protect the quantum processor. The entire system is encased in a vacuum chamber. By removing all air molecules, we eliminate convective heat transfer that would otherwise warm the inner components. Finally, we use nested radiation shields to block infrared heat. These gold-plated shields catch and sink radiant heat before it can reach the quantum processor at the center. Superconducting qubits are extremely sensitive to magnetic fields. Even the Earth's natural magnetic field is strong enough to cause decoherence. To mitigate this, we use specialized shields made of materials like cryoperm or mu metal, which redirect magnetic flux lines away from the chip. At the lowest temperature stages, superconducting enclosures, such as aluminum cans, utilize the Meissner effect to perfectly expel all internal magnetic fields. Now let's discuss the challenge of routing control signals into this deep freeze environment. Standard copper cables are excellent heat conductors. If used as is, they would act as thermal highways, funneling heat into the fridge and crashing the system. To solve this, we use specialized materials, cupronickel or stainless steel for higher temperature stages, and superconducting niobium titanium for the coldest stages. Even with these materials, we must thermally anchor cables at every cooling stage, physically clamping them to siphon off heat before it reaches the QPU. We also use inline components like attenuators, filters, and isolators to clean up the microwave signals and prevent noise. Attenuators reduce incoming signal strength to dump thermal noise, while low-pass filters block unwanted radiation. Isolators act as one-way valves, allowing the readout signal to exit the QPU while preventing external noise from traveling backward. The processor itself is mounted to the gold-plated mixing chamber plate, ensuring perfect thermal contact at 15 millikelvin. The final packaging houses the chip, providing the last layer of shielding and dampening against acoustic vibrations. As we scale to thousands of qubits, our current wiring methods face a, quote, heat load crisis, where total cable heat exceeds the cooling power available. Solutions include building larger high-capacity superfridges and integrating cryo-CMOS electronics directly into the 4 Kelvin stage. Thank you for joining this overview of quantum cryogenic infrastructure. We hope you have a better understanding of the extreme engineering required for quantum computers. If you are interested in discussing these concepts further or exploring professional collaboration, please feel free to reach out via email or connect through the CQT Web Hub and LinkedIn. Thank you for watching.